or constant temperature process. Consider an ideal gas in a piston cylinder arrangement. The heat is supplied at constant temperature, which is shown on the PV plane as an isothermal curve represented by PV is equal to constant. Let M be the mass of the gas considered in the piston cylinder arrangement. Writing the first law of thermodynamics, for infinitesimal change of state or very small change of state, which is written as delta Q minus delta W is equal to du. Since the process is assumed as reversible, delta Q can be taken as TdS, because delta Q is equal to TdS holds good for reversible process only. And also delta W can be taken as PdV, because the process is quasi-static or the reversible and the system is closed. Delta W can be taken as PdV. Substituting these two in the above equation of first law of thermodynamics, we get TdS is equal to du plus PdV, implies ds is equal to du plus PdV by T. But for ideal gas like air, du will be taken as Cv dt. Hence ds is equal to Cv dt plus PdV by T. Integrating both sides, we get S2 minus S1 at constant temperature is Cv log T2 by T1 plus R log V2 by V1. That is by replacing P by T with R by V, because working fluid is ideal gas, P by T is R by V. So this is the change of entropy for isothermal process. Considering the fourth process, that is adiabatic process, in which heat transfer is zero. Adiabatic means perfectly insulated, perfectly thermally insulated. Q should be zero. Then any process can be treated as adiabatic process. Consider an ideal gas in a piston cylinder arrangement. The system is perfectly thermally insulated so that heat transfer is zero between the system and surroundings. But the gas could do work adiabatically on the surroundings at the cost of decrease in its internal energy. The process on the PV plane is represented as a steeper curve 1 to 2. The equation of the process is PV to the power of gamma is equal to constant. Now, taking the equation ds is equal to delta Q by T for the reversible process. That is the definition of the change of entropy in any process. ds is delta Q by T for the reversible process. Because delta Q is 0, implies ds should be 0. That is S is equal to constant for reversible adiabatic process. Hence, any reversible adiabatic process is known as isoentropic process with a constant entropy, which is indicated by a vertical line on temperature entropy diagram. If the adiabatic process is irreversible, then entropy of the system would increase, because the irreversibilities shall generate heat like friction. Hence, entropy increases. That is, in general notion, delta S in any adiabatic process is greater than or equal to 0. Delta S is equal to 0 for reversible adiabatic process. Delta S is greater than 0 for irreversible adiabatic process. Now, considering thermodynamic universe, which is the combination of a thermodynamic system and the surroundings. Now, I suppose the system has undergone a thermodynamic process. By exchanging heat with the surroundings. Let the heat would be rejected from the system to the surroundings. Then, if the process is reversible process, delta S of the system plus delta S of the surroundings, this should be the algebraic sum, that is delta S of the universe should be equal to 0. That is, in the above process, the decrease in entropy of system should be compensated by the increase in entropy of surroundings. The net effect being change in entropy of universe is 0, provided the process is reversible. If the process is irreversible, then entropy of universe would always increase. Combining, we can write that delta S of the universe is always greater than or equal to 0. That is, the entropy of universe tends to be maximum. This is the second law of thermodynamics. Now considering the polytropic process, which is indicated or given by the equation Pv to the power of n is equal to constant, where n is the polytropic index. Writing the first law of thermodynamics for the polytropic process, for infinitesimal small change of state, that is delta Q minus delta W is equal to du, and assuming the process as reversible, delta Q is equal to TdS. This is the second law of thermodynamics. Delta W is equal to PdV. We get TdS is equal to du plus PdV. This is important TdS equations. By combining the first law and second law of thermodynamics, ds is equal to du plus PdV by T. Du can be replaced as Cv dt, and P by T is R by V. Therefore, ds is equal to Cv dt by T plus R by V dV. Integrating, we get S2 minus S1 is Cv log T2 by T1 plus R log V2 by V1. For isothermal process, since T1 is equal to T2, log 1 is 0, S2 minus S1 is R log V2 by V1 or R log P1 by P2, or even it can be written as, because R is Cp minus Cv, log P1 by P2 for isothermal process. This is a change in entropy for isothermal process. Whereas S2 minus S1 is equal to Cv into log T2 by T1 plus R log V2 by V1 holds good for any thermodynamic process between two given end states 1 and 2. Now let us consider an objective question. The relation du is equal to TdS minus PdV is true for A, reversible processes only, B, irreversible processes only, C, all processes, D, a reversible cycle only. The above relation is the relation among the properties, because internal energy U, temperature T, S entropy, pressure P, specific volume V, all are being properties. It is the relation among the properties. Therefore, the relation among the properties between two given end states shall be the independent of the path followed. Hence, the relation is applicable for all thermodynamic processes. Answer is C. Next objective question. The entropy of a system A can never decrease, B can never increase, C may decrease, D may increase or decrease. The entropy of a system would increase if heat is supplied to the system, and the entropy of a system would decrease if heat is rejected from the system. Therefore, the answer would be D, based on whether heat is supplied to the system or rejected from the system, entropy may increase or decrease. Next objective question is, suppose a system undergoes an irreversible process. Then the change in the entropy of the system is given by A, ds is equal to delta Q by T, B, ds is less than delta Q by T, C, ds is greater than delta Q by T, D, ds is equal to 0. Because the process is irreversible, the change in entropy ds would be greater than delta Q by T. Answer is C. If the process had been reversible, for reversible process, ds is equal to delta Q by T. In general, for any differential change of state undergone by the system, ds would always be greater than delta Q by T for any process. Next question. An irreversible process can be characterized as A, it proceeds such that the system is always in equilibrium with its surroundings. B, it cannot be reversed without causing permanent changes in the surroundings. C. A spontaneous process which proceeds in one direction only. D. A process which, when carried out in the reverse direction, restores the system as well as its surroundings to their original states. Looking at the options, an irreversible process would never be, an irreversible process is that process which cannot be reversed without causing permanent changes in the surroundings, because in the irreversible process there would always be some mechanical friction or viscosity or eddy currents or turbulence or electric resistance. Any one of these irreversibilities would exist, because of which the system cannot be reversed without producing permanent changes in the surroundings. Answer is B. The C is also the answer, because all irreversible processes are spontaneous in nature, which proceed in only one direction. For example, heat transfer through a finite temperature difference is an irreversible process. For example, the mixing of two different gases is an irreversible process, because once the gases are mixed, we would never get by themselves the independent gases. The gases would never get separated by themselves. So, the mixing of two different gases is an irreversible. The passage of electric current through a resistance, it is a irreversible process. So, all irreversible processes are spontaneous in nature, which proceed in one direction only. Therefore, there are two answers, that is B as well as C. Coming to the next objective question, a reversible engine absorbs 1200 kilojoules as heat from a source at 600 degrees centigrade and delivers 600 kilojoules as work and rejects the rest of energy to a sink. Determine the sink temperature. The solution to this problem can be given as, because the engine is reversible, or maybe taken as Carnot heat engine, thermal efficiency of any reversible heat engine can be given as the temperature of the sink, 1 minus temperature of the sink divided by temperature of the source, which is equal to the work output of the heat engine divided by heat supplied to the engine. It can be given as 1 minus temperature of the sink divided by temperature of the source is given as 600 Celsius plus 273 is equal to 600 divided by 1200, that is 0.5. Thermal efficiency of the engine is 0.5 because work output is 600 and heat supplied is 1200, from which temperature of the sink can be obtained as 436.6 Kelvin. Next question can be taken as, the question is on throttling process. Throttling is an irreversible adiabatic process. The question is given as, during a throttling process, the entropy of air increases by 13.38 kilojoule per kg mole Kelvin. Determine the ratio of the initial pressure to final pressure. The solution to this problem is given as, the change in entropy of ideal gas, which is like air, during any change of state is S2 minus S1 is equal to Cv log T2 by T1 plus R log V2 by V1. During throttling process, for ideal gas, delta T is 0 since Joule-Thomson coefficient mu is equal to dou T by dou P is equal to 0 for ideal gas. Therefore, the change in specific entropy could be given as R log V2 by V1. Because he has given 1 kg mole, the change in entropy for 1 kg mole of air can be taken as universal gas constant capital R into log P1 by P2, because V2 by V1 is equal to P1 by P2 since temperature is constant for ideal gas in throttling. Therefore, S2 minus S1 is given as 13.38 is equal to 8.314 into log P1 by P2. Natural logarithm. Ln means natural logarithm. Implies P1 by P2 is equal to 5. By taking anti-logs on both sides, P1 by P2, the pressure ratio is obtained as 5.